Good morning, organic chemistry. How are you today? I am so excited for this video. I'm actually going to share this with both Organic 1 and Organic 2. We've got organometallics as a topic in both courses, so I wanted to kind of try something different. Let's take advantage of this online situation that we're in. And I want to kind of work my way through metals in general, and I'll highlight which course we'll see both our metals in, whether it's both Organic 1 and Organic 2. And then I also want to give just a little bit of background and a little bit of history with each one of those. And I'm going to post this document as well. Just like our other documents, if you check it out. Oh, this is Sparkle Pen moment. I've got a ton of web links in there. Now, this isn't meant to be intimidating, that every single link on here is going to be on your test. That's not at all the case. I actually just want you to have this for later classes as well, and other classes that you might see your organometallics in. So let's pause for a second. This is relevant for both classes, 2323 and 2325. Why in the world do we have organometallics? Why are they their own subject? Why do we give a crap about them? And how long have they been around? What are they good for? So let's take the first page just to give us some background information, and then we'll get into some specifics. So why organometallics? So it turns out that organometallics have been around for 120 years. Now, these are combining our normal organic processes with some of our metals. And there's some really good reasons why organometallics have been used in organic chemistry. And then, again, we are going to translate this. We can translate this all the way up to biochem and into biological processes. So why do we even care? Why do we care? So organic chemistry, now that we've had some of our mechanisms and we're starting to learn what we can actually do for organic chemistry, we've had two main types of mechanisms already. We've seen polar mechanisms, and those are our two arrows that we draw, two-headed arrow. Those are two electrons at a time. And we've had a little sprinkling of some radical reactions, and those radical reactions have just one electron at a time. Well, let's call those our kind of normal conditions for organic chemistry. And they follow a set of rules. For every one of these reactions that we've learned, we've followed a set of rules set up by Mother Nature. And what's really cool about organometallics is that they let us do reactions that are not possible under these two circumstances. And our first organometallics, the original, Grignard, is going to show us that very clearly. I'm going to show you that on our next page. And so what's pretty cool is we can also take our normal reagents, so things that we've learned in our polar mechanisms, and we can drastically alter their reactivity with a metal. That's also going to be evident in our first reaction, which is a Grignard. It's pretty cool. And then to a synthetic chemist, what's awesome is that they tend to be highly specific and highly specialized. Okay, this is phenomenal. We'll see in all of our metals chemistry that they are highly specific to one type of bond, and that is exactly where they go. And they tend to be quite high yielding and very specialized. And that is extremely hard to do for synthetic chemistry. My OChem 2 people, think of a mixed aldol. All right, you can take two ketones and mix them in that mixed aldol and come out with 16 products. Imagine if you could put a metal in there and come out with one product. It's quite awesome. And the metals can also help us do multi-processes in just one step. They're actually pretty amazing. So I can't wait to share them. Now, our mechanisms are going to look a little bit different. So I'm going to add them to our list of possibles. But keep in mind that I just want to give you some vocab. I would never test us on the actual mechanism for an organometallic. This will be in your inorganic class. I know y'all are chem majors now. And so your next course, your inorganic course, you're going to learn these pathways. I just want to show you one in this video so you can learn the language a little bit and kind of learn why why these things happen the way that they do in a very basic way, but I would never test this on the actual mechanism. You can always spot organometallic mechanisms and mechanisms with our metals because they look drastically different. Remember our general mechanisms for organic. We use arrows. We use our double-headed arrow or single-headed arrow for polar or radical mechanisms. And we tend to go in a flow. Like a nice SN2 mechanism, we go in a nice flow with our arrows, and we work our way through that pathway, and it's all based on kinetics and transition states. For our organometallic mechanisms, they actually work as a process, and there are three main kind of steps that could happen in an organometallic process. And within that process, it's pretty cool. The first thing that you can sometimes see is called a ligand exchange. Now, our organometallics bond a little bit different. I'm going to show you that in a second. So you can actually have some weaker bonds, not just ionic and covalent. Remember from Gen Chem, there are actually 5 types of bonds, not necessarily only ionic and covalent. Those just happen to be the first 2, but there are coordinations and different 3 other types of bonds, and you hit those in your organometallic chemistry. Excuse me, I'm feeling my allergies today. Sorry, y'all. All right, and then our ligand exchange, I'll show you one of those down here in a second. And then what's really fun about organometallics is they tend to do 2 things within the cycle. So you might have an oxidative addition first in your cycle, but somewhere later in that cycle, you must have a reductive elimination. They work in partners. You will always find both of them in that process. And then we've got another partnership, and that's a migratory insertion and a beta hydride elimination. So both of those you'll see quite often in your pathways, and they work as partners. If you see one, you're going to see the other, typically. Okay. And then how do metals work? So I just want to remind us, if we're in the transition metals, we are not in normal covalent bonding rules anymore. In fact, our transition metals are hitting the d orbitals. So we have to think of d orbitals. You know, our covalents, especially for organic, if you're dealing with carbon, nitrogen, you know, any of those, you're hitting that octet rule and you're in the p orbitals. But for our transition metals, and not every example today is a transition metal, but for any that are transition metals, they can actually bond up to 18 electrons. Our transition metals can do quite different things in their bonding than what we're used to for carbon and hydrogen. So as you get into organometallics and you take an inorganic class, you're going to learn something called the 18 electron rule, or an 18 electron count. And I'm going to just give us the basics for that. Why do we care? It means in our metal, when you have something like your transition metal, like I just gave a generic here, rhodium. Let's say our rhodium looks like this, and we've got some bonds to rhodium here. Our rhodium, if we have all electrons, all of our 18 electrons there around our rhodium, then this complex is considered saturated. So this is a big vocab word. If your metal has the 18 electrons already, it is saturated. I like to think of metal sometimes as like a big docking, area. If all of your docks are full, nothing can come in. If you're fully saturated and you have 18 electrons already around your metal, nothing's going to happen. You're already full. Kind of like planes pulling into a terminal. All of your spots are blocked. Nothing's going to happen. A lot of metals are sold saturated 18 electron. They're a little bit more stable that way, so they're shelf stable. But then what happens is that first step, that ligand exchange, so you may lose a ligand. One of these ligands might pop off, and then now what happens is now you've got some space. So now our rhodium might be down to 16 electrons instead, and then now that's considered unsaturated, another vocab word there. And if you are missing some electrons, well, now you're in business. Now you can start doing some pretty specific chemistry. And then you'll notice that our pathways, and again, this is super general, like don't go take this to another class and write it on your test, you'll probably get it wrong, but this is just an example to show you some vocab. So if your metal now is unsaturated, now we get the highly specific part of our chemistry. So now we can do one of those insertions, and rhodium can insert this double bond. And then you'll notice, look at our arrows. Our arrows are not showing electrons. Our arrows in this case are showing a pathway. And it's going to show us that both of those, we've got an insertion, and then we're going to have here, we've got an oxidative addition followed by our partner, remember, for our oxidative addition, and then we've got a reductive elimination right along in there. So your arrows aren't showing necessarily your track of electrons, they're showing the pathway and the full cycle that your metal goes through. So your mechanisms, you can always spot right away for your metals. They will be in a cycle. Do you ever wonder why sometimes in your bio or biochem you see these cycles and not a push of electrons like we draw in organic chemistry? So you can spot them right away. And then the other vocab I want to show you is that, again, we don't always have just a straight covalent bond for organometallics. We sometimes have a coordination bond. And those typically are drawn like this. So do you see that perpendicular bond to that alkene? That is going to be a coordination bond. You can also spot your organometallics that way. They can bond like we normally draw, but then they also can coordinate, and those bonds tend to be drawn perpendicular like that. So let's draw that in. All right, so I just wanted to show an example just so you could spot organometallics in those pathways. My Organic 1 students, you've got a pathway for grubs in your textbook, and I'll probably post that pathway for you on your Blackboard. My Organic 2 people, you'll start to see these pathways in your biochem a little bit later, and we may not draw these pathways for some of our metals. I think we're just going to use them, but you can spot these pathways right away. And then I gave you some links, so if you've got some metals in later classes and you really want to count your electrons, and it's actually really fun to go through an electron count and try to figure out if you've got 18 or 16 or 14 even, and if your metal is going to react like that or not. And so I gave you some links there, and then I gave you a big main. MSU has an online textbook for organic chemistry, and I gave you a link to that for their organometallics section. They tend to just list a bunch of the reactions in there, so if you're seeing this in later classes, my OChem 1 people, if you take OChem 2 in another college and you're getting a bunch of metals, here's some good resources for you. All right, let me pause here because now we're going to get into specifics, and I need to keep my videos under about 20 minutes. So I'm going to stop here and start to post this one now that I feel like we've got a little bit of vocab, and then we're going to get specific. We're going to roll down a page and start way back 120.